Here we are in Canada, from 5 continents, people talking about C++, and one of the questions that you might have heard quite a bit, especially over the last decade, is anybody who hears what conference you're going to will pick out roughly one keyword out of it. And how many of you have been asked, sometime in the last 10 years, why are you still doing C++? We've been seeing that quite a bit. The answer is performance per dollar. C++ is unmatched by any language other than C, where it wins because of abstraction, in terms of getting performance per dollar. In fact, C and C++ and Fortran are in that game and are the kings of that game, and Fortran for specific kinds of tasks especially. Let me talk about why this matters more than ever today. There's 3 specific aspects of performance per dollar I want to focus on. The first is power, performance per watt. This is a key driver I'll talk about in the next few minutes at all scales. It is a key driver on mobile devices, we know that. It is also a key driver in the data center, and as soon as you've got those 2 endpoints, you know what a pincer movement looks like. And that's all blowing back into every single kind of system in between. And that is a long-term trend that is not going away, it is only going to accelerate. The second aspect of performance per dollar is performance per transistor. Or I have this much die area that I can put transistors on, and Moore's Law is still letting me pack more in, although there's a note we want to say about that later on. But how much performance can I get? Because especially in mobile devices again, I can only physically put so much into the package. If I want to do more, I have to do more with less. What language comes to mind for those kinds of demanding applications? And also performance per cycle. Every bit of juice I can squeeze out of a modern processor is important, especially to enable new experiences. Something that we as an industry have been pathetic about for the last 15 years and have just been getting good at again. So let's talk about those experiences, bigger experiences on smaller hardware, and where pushing the envelope means every cycle matters, and then a programming language that lets you get every cycle matters. Just looking back at a brief history of C++, this all began when Bjarne in the late 1970s, 79, and throughout that first decade to 89 worked in AT&T on C with classes, which then became ARM C++, the annotated reference manual that was the basis, the working document beginning for the first standard. It started getting adoption slowly then, but that really grew in the next decade, the second decade of C++'s life from 89 to 99-ish. Where C++ goes to the mainstream. There is large-scale, massive industry investment in C++, in compilers and tools and development. It also went to ISO standardization during this time. The first C++ standard shipped in 1998. It went to space in the Mars rover, and almost any kind of demanding application used C and C++. The third decade was interesting, because the third decade was the rise of managed languages that favored productivity over performance. And that is a perfectly valid trade-off. Let me put that up right up front. There is absolutely nothing wrong, and there will always be a place for languages that value productivity over performance. But the reverse is also true. There will always be a place for languages that favor performance over productivity when they're in tension, and they're not always in tension. var in C# and auto in C++ OX are just as convenient, and we do it in C++ because it doesn't cost you anything. So we'll talk about that emphasis. But with what I've heard some people call coffee-based languages, I like that term, so I stole it shamelessly. With the rise of the coffee-based languages, a key question became asked. One that I heard a lot in developer division at Microsoft, and I heard a lot in other places throughout the industry. Our C and C++ is native code just for device drivers and operating systems. Is it basically uninteresting anymore because we'll be able to do everything we need to do in managed languages? That is a question that stood, and people had different opinions, but stood largely unanswered for a number of years. So let's take a trip back in time. Back when I joined Microsoft, Windows Longhorn, which later became Vista many, many years later, was under development. And one of the first things I learned being immersed in that culture as a C++ person was that not just the developer division was very heavy on managed languages, which was the new thing and being developed, and it was great, cool stuff to be working on, but also that there was more and more of a belief that managed languages could do everything interesting that you would ever want to do. And in fact, Windows Longhorn became the poster child in the entire history of our industry for pushing managed language to their limits, because it was the only large-scale effort I have ever heard of, and maybe remain the only one, that tried to put managed code at the heart of an operating system, to the extent that when I joined Microsoft, shortly after I joined, the edict went out internally saying all new Windows APIs will be managed. You can have native ones, but that's in addition to managed ones, not instead of them. So this was an all-in bet on managed languages. We feel they're ready for prime time to be a real operating system level interface. So this is a very interesting challenge. It turns out that the fit wasn't perfect. Managed languages do not yet have the robustness, nor the performance, nor the deployability and serviceability required for really demanding applications like operating systems. And so now, although there are many cool managed interfaces there, the primary Windows OS services are still C and C++, and that's likely to stay that way. Not because managed is bad, it's perfectly appropriate to have wrappers over those for productivity-oriented code, but because it's wrong to think here's one tool that can do everything. It can't, so it's important to know each tool's limits. So that was an interesting shift because we learned a lot from that. Now, during this decade where people tried to make this shift into pushing managed languages as far as they could go to see if it could be done, another interesting thing was happening. You might say another interesting thing was not happening. Innovation in user interfaces. In the early to mid-90s, we shipped mice and Windows to everybody, and we called it good for 15 years. If you wanted new user interfaces, you had to go watch Star Trek or go watch Minority Report. Because Star Trek, you had this nice tablet that you could just visualize anything on. In Minority Report, you could just gesture at something with gloves and have it do the right thing. And we got lazy as an industry. And that sort of is related to the rise of managed languages because we failed to continue demanding from our systems. We said, enough is enough. All we'll ever need is a keyboard and mouse. Because of that, there was less pressure for demand because systems still got more powerful during that time period. And so managed languages seemed to have all this extra slack that they could count on to save them when all the performance wasn't accessible because it wasn't required. Well, now we have wonderful tablet experiences where we know that the device is supposed to morph into becoming the application. Immersive applications. We now have augmented reality applications like Word Lens that will let you in real time pan around, look at a scene, and it will automatically translate signs for you and overlay them. So I don't know if you've looked at Word Lens. If you haven't looked, there's a Google video, a YouTube video about it, where what they do in real time is they use the camera to acquire the image. They use OCR to figure out where the text is. They do automatic translation to translate that text from source to destination. They then take the translation, overlay it on the position of where the original text was to replace it in real time on an iPhone. If that's not a demanding application and a new user interface and shouldn't make us dissatisfied with just clicking on buttons, I don't know what is a poster child. And this is only one of many. Of course, I have to mention Connect, because it used to be Minority Report interfaces were the thing of movies with Tom Cruise in them. It only took, 3 years to become mainstream. That's scary, but it's also really exciting. So when we look at those things, I want to quote, I don't often quote from myself, but I will this time, so indulge me. When I wrote the Free Lunch is Over article about the shift to multi-core computing, one of the things that I said is, what are some consequences, what are some predictions, was that efficiency and performance will get more, not less important. The languages that lend themselves to high performance, because single core performance is starting to level out, still increasing, but not exponentially, will find new life, and that is exactly what has started happening 2 years ago. It is exactly what started happening inside Microsoft 2 years ago. So when you hear the term C++ Renaissance, that started in developer division because of the realization that we need managed and native, and both are crucial. Expect long-term increased demand for performance-oriented languages and systems. Let's see why this is exactly coming true. By the way, here's a new slide I happened to see a couple of days ago on Slashdot. If you read that, you might have seen people ask things like, was .NET all a mistake? These are questions people would not have asked in 2005. And it's interesting that this is only one example of many, many places. The answer to the question, of course, it's a stupid Slashdot question, because it's intended to provoke. Whereas the answer was, of course it wasn't a mistake. .NET and Java are important. But it's not at the expense of C++. They can't do everything, nor can C++ do everything. You need to use the right tool for the job. So during this lost decade, where we didn't innovate in user experiences, and we tried very hard to make managed be the single tool that could do everything, the hammer that made everything look like a nail, because it's all we had, we have now begun, as of about 2 years ago, to see a C++ renaissance. There is increased demand for C++ programmers. There is increased training. Everything from swaptions to medical imaging to all sorts of things require demanding native code. And fundamentally, the reason for this resurgence of demand is because the return of the king. The issue that has always been king in the entire history of computing, except in those 10 years, which is that performance per watt, per transistor, per cycle, performance per dollar matters in a lot of applications. So let me start with a short reality check. If you were to complete this sentence, the world is built on, and pick your programming language, what's the right answer? Java, all of them? You know the answer I want to hear, so go ahead. C++, right. Actually, that's not my answer. My answer is C and C++. Now, it's interesting you mentioned Java, because Java clearly, you could make a case that a lot of the world is built on Java, or JavaScript, I would say, is even more important than Java, actually, because of the browser. What are they implemented in? You guessed it. What else? COBOL. That used to be, right? So I can't say COBOL is built on C++, but neither is the world built on COBOL, so it doesn't win either. Fundamentally, the entire world is built on those two languages. One is a superset of the other with stronger abstraction. And that is an important fundamental thing to remember. So let's take a look at where the focus was. Now look at four specific things. Efficiency, getting performance per dollar, that's that first column. The flexibility, the ability to express what you need to express. The ability to have strong abstractions, specifically templates and generics, so object orientation as well, objects and generics. And then productivity, the ability to have the programming language and environment do more things for you so you don't have to worry about it, possibly at the expense of the other columns. C is all about the first two. It did not even try to get strong abstraction, nor did it try to get productivity in the way we think about it today. It was all about efficiency and flexibility and being able to get that in a portable way, which was not possible at the time. What Bjarne did with C++ was he said, we want to double down on that bet. And we want to have our cake and eat it too, because I'll bet you I can show you how you can get classes and generics without overhead. And by goodness, he did it, and that's why we're all here. Then the managed languages focused mostly on productivity. They also did a really good job at abstractions, at classes, and then generics, which are now in both Java and in .NET as the two major managed platforms. But they did it at the expense of flexibility and efficiency, because to them, programmer time was the thing to be optimized for. So this is where we're going to put our investment. We believe that this supports this, so we're going to double down here. But we think metadata is more important. Making sure metadata is always available, whether you need it or not, is more important than the overhead it incurs on code that doesn't need it. We think that garbage collection all the time, whether you need it or not, because you don't always need it, even in C# when you say using, or Java with the dispose pattern, having it there all the time is required, is worth it, even at the expense of overhead on programs that don't need it. Talk about startup time. How long does it take to spin up a Java or C# application? Fairly short, but long compared to C and C++ native code. JIT compilation, all of these kinds of services that impose overhead on programs that don't use them, but really do help productivity. That's their play, and they did a very good job at it, and that will continue to be important as well. But that first column has been king from the beginning of computing until about 1999, and again since about 2 years ago. Except for that lost decade, the first column is king, and the king of those is C and C++, one of which is a superset and has stronger abstraction. I noticed this on the intertubes recently, and again I'm just pulling anecdotal evidence because there are many of these that fly by, but just to illustrate. So here's a code on Microsoft's MSDN site about creating an IE add-in using C++ and ATL. Okay. What's interesting is that this was written by a managed guy who spends all his time doing WPF and C# and those kinds of things in Silverlight, and that it was written in the past year. This was not something written back in 2002. And I like this because he sort of feels like he has to apologize for using C++. No, it's not because I hate myself, but because of the flexibility and the performance of the language. It says if you want to write an add-in that's not trivial, you will want to do it in C++. And that is now our advice again to developers. Just as an example, I'm not going to go deeply into these slides, but here's why performance matters. Anytime I give a performance talk about optimization on current hardware architectures, here are some of the things I hit. I talk about how cache-conscious design is important, locality is important. You want to keep data that's not used together apart, because then when it's used on multiple cores, you don't get false sharing on cache lines that ping-pong back and forth, and you get enormous drains on performance because of cache effects. Second, you want to keep data that's frequently used together close together so that you minimize your cache footprint, but you also get better packing. So when you ask for a byte, the bytes around it and the cache line you get are also things that are interesting to you rather than just filling up your cache. And you want to keep hot and cold data apart. Even if these two pieces of data are frequently used together, if this one's used 100 times for every one of these, you want to keep them on different cache lines again and different memory pages so that you're not paging in all of this when all you need is this part. How many of us knew nearly all of that already before we got here? You don't have this control in managed languages. You cannot generally do this. Follow this advice in managed languages. Now there is a caveat. You can go to arrays and array lists. You can, but you have to work hard and work against the language and against the automatic facilities, including garbage collection, which will happily compact your data for you so that you inject false sharing when you didn't want it. You have to be much more careful about padding so that when the garbage collector compacts, you don't suddenly get sharing and the system starts out fast and then degrades and you don't know why. You're just spending a lot of time in cache coherence, and there's no obvious reason why that's the case. Because C++ gives you power and control over exactly where memory goes. Another reason for this is when you have arrays of data and you traverse them in linear order, it turns out the short version of the spiel is not only do you have better overhead, better compaction, so less overhead per node, per element, so that you're further left on this cache size. You may fit into 1 meg instead of 2 or 4 meg of cache, so you're further left and you get better memory performance. Even more important, because if you're going to traverse the whole thing, you traverse it linearly in memory. It turns out you can get way, way, way better performance with a prefetcher, which acts as an infinite level of extra cache, of infinite size, a level of extra cache, if you access things in memory order. Don't even bother if you're doing a node-based, node-chasing container in memory, which is the default in managed languages. Don't even bother. You can only get this with arrays. And the key is, arrays and vectors are more compact, they're further to the left, but also on lower curves if you're traversing the whole thing than lists and sets. We teach this to people, but you can only actually act on it fully if you have full control over memory layouts. That's why the world is built on C and C++. Now let's talk about mobile, because that's where performance per dollar, especially performance per watt and transistor, is really important. If you look at mobile requirements, battery, performance per watt, size, performance per transistor, and bigger experiences on small hardware like augmented reality and all those cool things means every cycle matters. Every single one of those things comes into play here. So let's take a look at where the mobile industry is. Here are some familiar people. How many of you own at least one Apple device? Yes, that number has been going up a fair amount. How many of you own at least one Android device? Catching up. Still also growing. How many of you own at least one Windows device? Good, not yet less than iOS, so this is good. If you look specifically at mobile, at phones, they call them phones, but come on, it's a small computer with a cellular radio. The phone is an app. But let's call them smartphones, or play along. These so-called smartphones are cool. They give new user interfaces. They copy from each other like mad. They invent. They make our lives much easier and convenient. And what are they built on? Well, in version 1 of every single one of these devices, what was the story for writing apps on the phone? Well, in iPhone version 1, there was none. All you could do is use web apps. With Android, the answer in version 1 was Java. That's all you could do. You could write apps in Java. The same thing was true in Windows Phone 7. If you wanted to write an app, you could do it only in a managed language, in C# typically, but on .NET. What is version 2 of each of these platforms doing? Well, we don't know yet for Windows Phone 7. We do know that iPhone went to Objective-C, C, and C++ as their entire story for apps, and those are all native code. Those are the only 3 supported languages for writing iPhone applications. Android still supports Java, nothing wrong with that, but the native development kit is essential when you want performance, and that means access to C or C++. And we'll see what happens with Windows Phone 7. Just looking at what's been happening, the trend is clear, at least on these first 2 platforms. If you want to get full power out of the device, you are writing native code. And there is only one common denominator here, and that is C++ and C. In fact, if you look at where Apple is investing its time and energy, have you noticed the Clang project? How many of you are familiar with Clang? So Apple has been investing heavily, and now other companies as well, in making a new open source C++ compiler. I don't know if it's ever built this way, but it sure looks to me like a GCC killer is the intent, or a replacement, or alternative. Let's say that, that's nicer, alternative. And as of a year ago, that builds Boost, so yay Apple. And oh, by the way, Google is investing heavily in this as well. They use it for their very large and demanding C++ code bases internally for code analysis and quality. And just as of a few months ago, for their monolithic C++ code bases, one of the largest in the world, they're adopting that technology as well to keep it going, to do error detection and diagnostics and code quality. All again, investing heavily in Clang. So if you looked at what compiler has been invested in the most with actual real dollars in the last 2-3 years, you could argue whether it's, say, Visual C++ or GCC or Clang. All 3 have invested in heavily, but that's the list. And certainly the newest compiler that is getting the attention and mindshare and investment is a C++ compiler, which now supports much of C++ OX already. Just a note about native applications. So Google Plus was announced. Sorry, Andre. Andre's at Facebook. And because Google is great at the web and has this nice web app, you would think, oh, it doesn't need a native app. No. The reason I point this out is because native apps do not replace web apps. Web apps are for reach. Therefore, when you don't have a native app, but the native app is preferred, the web app is the backup. That is the model we are more and more going to. You have both, the web app for reach when you don't have the native one, but you really prefer the native one. Why? Power, performance, native code. Now let's talk about the data center, where performance per dollar also matters a lot. James Hamilton, ex of Microsoft and now at Google, did an excellent analysis of costs of data centers and servers. And what he did is he went through for a 3- and 10-year infrastructure amortization of what are the costs of running a modern world-class data center. such as he had had personal experience with in several companies. And he broke it down. It turns out, you might have heard the meme that says power is the biggest cost. Well, that's actually not true, and that's what he debunked here. It's the second biggest. The biggest cost is the hardware. 57% is the cost of the actual server hardware. Of the rest, the green 18% is the power distribution and cooling, and the purple 13% is power, but that means you should take those two together, because the power cost is 18 plus 13. In fact, let's take a closer look at this. If we take away other costs and we look just at costs of hardware and power, that is roughly 88% of the cost of running a data center today. The hardware, the servers, and the power. Because when you think about power, you should also talk about not just here are the watts the chip consumes, but what's the cost of getting the power to the server? What is the cost of taking the heat away from the server, cooling? And that's all part of delivering and using the power. 88%. Why is that a very interesting number? Well, because it means that there are 80% of your costs of a data center that are directly related to performance per dollar, performance per transistor, performance per watt, that you improve using a more efficient language, a more efficient program. So if I make my code run in half the space and time, so I need half the compute power, I can immediately lop off 44% of the cost of a data center. It's actually a little bit more because you can save some of the other infrastructure costs too. Not the bandwidth, because you still need the bandwidth. But immediately you get a twofold improvement in efficiency of your program. Gets close to a twofold improvement in your total cost of running a data center. That is so different from the 1990s and 2000s. Because as he concluded, notice his conclusions, which I'm merging from two of his talks. He had a couple of versions of his talks, and I'm merging them together here. He said all of these things. He compared the enterprise, the way we've been doing the enterprise, you know, server rooms, to the cloud, data centers. And he said there's three differences. The first is people costs went from being dominant in the data center, where your admins and your programmer time was the dominant cost, to being nearly irrelevant. They don't even show up on the pie chart. 88% of it is just power and servers. People don't even show up in the pie chart. That includes your sysadmins and your programmers. Don't even appear as a cost at that resolution. Second, work done per dollar and work done per watt are what really matters, and his words are software issues dominate. That's because efficiency is king for managing costs of a data center. It matters in real dollars and billions of dollars. And his third point, which is very interesting, is he says, see what's happening over here in the data center? Expect all those techniques to go right back to the server room, right back to desktops. And we're already seeing it happen. If you look at that first bullet, people costs, programmers and admins, when that is important, that is where productivity-oriented managed languages really shine. If your biggest cost is programmer time, you want to invest in saving that. Who cares if you spend a few more cycles on GC? It doesn't matter. That's not your cost, or on metadata, or on anything else. Your cost is programmer time. That's what we optimize for. We're optimization geeks, right? We know how to optimize. So do finance people. They also know how to optimize. Look, there's my hotspot. Let's optimize that. Not the case anymore. So there's good news, bad news. The bad news is we're no longer the biggest cost. The good news is people who know how to wring performance out of these beasts are in high demand and are getting some exorbitant salaries lately. If you've been seeing some of the poaching going on between high-frequency trading firms, where C++ programmers are getting poached for seven-figure salaries. Like, when was that in the news ever before? Hardware and power, 88% of costs. That's where performance languages, native code really shines and lets you optimize real savings. And there's a blowback that we're already starting to see. Now, Bjarne did a very nice interview recently, a series of interviews, and one of them that he got a lot of flack for. He was saying to me in an email, saying, I got a lot of flack for saying that my biggest contribution to the global warming problem is C++'s efficiency. People are like, yeah, whatever. Well, so I asked him to elaborate his statement in email, and so he did. And here is his summary. My contribution to the fight against global warming is C++'s efficiency. Just think if Google had to have twice as many server farms. Each uses as much energy as a small town. And it's not just a factor of 2 efficiency. Efficiency is not just running faster, running bigger programs, it's also using less resources. Notice how he has hit in that email every single one of the 3 pillars of performance per dollar: performance per watt, performance per transistor, performance per cycle that we've been talking about. I didn't originally have a section on server and desktop because we talked about it, it'll blow back into the mainstream, and I was going to leave it at hand waving at that and not talk about it in detail, but I couldn't resist another article from Slashdot. When is the last time you saw a Slashdot article where people are paying attention to the power consumption of a desktop operating system as a competitively important feature? When is the last time you saw that? Don't tell me native code doesn't matter. So that brings us to the Renaissance. If you look at where bets have been placed, I added this slide later on because I couldn't resist adding at least one slide. So this is the slide I added here. In the 1970s, the industry invested enormous amounts of money in the first 2 pillars, mostly the first one, efficiency, and then in the second, in flexibility, by having a portable systems programming language, C, and an operating system built on it. So Unix and C, there were other things that were spent on, but they received an enormous amount of investment in that decade. Now, in the 1980s, there was still further investment in native languages in C and C++, but even more so in Ada and Smalltalk. And there now you're talking about going more to abstraction, to objects, and going more to productivity in those environments, because, well, safety is more important, or robustness is more important, for instance, in Ada's case. So there was still investment in the first 2 pillars, but more investment, some investment shifted to abstraction and productivity. Then in the 1990s, C++ was still heavily invested in. This is the boom decade for C++, where it really entered the mainstream. Everybody and their kid brother was writing and maintaining compilers, tracking the standard. The first round of standardization was going in full bore and finished. But we were also spending on Visual Basic and Delphi and Java, especially from 93 to 95 onward, at the same time as spending on C++. And then we have the lost decade, where we weren't doing as many innovative things. It seemed like maybe cycles didn't matter so much anymore. So let's really invest billions and billions of dollars in program productivity. And I'm not just talking about the people who provide Java and .NET compilers. I'm talking about all the people who consume them, deploy applications, build infrastructure. A lot of money went into this and will continue to. It's still important. It still has its place, and it's really good that this was developed. But for our next decade, expect to see a lot of investment here, because this is where the money is. This is where we can save much more money, where we can meet requirements we couldn't meet otherwise in mobile, where we can save money in data center, and all of that matters in the mainstream as well. So it's interesting to see where the money went. Follow the money and you'll see where the incentive is. Now, C++ OX, which will soon, we hope, be called C++ 11, is upon us. It has lots of new features, and it looks like that ballot is going to conclude on Wednesday. So on the last day of our conference, stunningly, it turns out is the day that C++ 11, it looks like, will be ratified. We may have the results the same day to report to you, we may not. But balloting closes, it's a yes or no vote. We expect it to be unanimous, and finally have an approved international second standard for C++ with 1 or 2 extra features. And as you look at these 1 or 2 extra features, this is not a complete list. It's not even a complete cloud. But I'm heartened by how many of you in your background surveys already said you are allowed to use these, because they're really important. For example, one of my favorites, Lambda functions. I was very pleasantly surprised to see more than half of you in your background surveys say, yes, I'm allowed to use those in production code. Good for you. The rest of you will follow very soon. Because many of us, including Microsoft, I'll talk about tomorrow afternoon, are shipping new technologies that require lambdas. You cannot write the code without them. Why not? Because we're designed for modern C++. Why not design it right for the next 20 years rather than have a compatibility mode for yesteryear? So more and more of these features will not just be available, but assumed and even required. So there's a lot there. We're going to talk a lot about C++ OX today, but C++ itself has not been sitting still. It may have been in the background, but it's really useful that this is the year that C++ 11 is being released. It is the year people are seeing a C++ renaissance. It is a year that is very special and exciting for C++ developers. I mentioned C++ Renaissance. Last time I looked, there were about 1.5 million hits, and that's been started by our good friends at Channel 9. Where's our Channel 9? Charles, can you wave? Yeah, so you're partly responsible for making this happen. So getting the word out there that, you know, C++ matters, we get it. So do Java and C#. But C++ really does matter as a first-class system. And when you take a look at all of those things and keep on seeing things like shining light on the dark matter, all this dark matter in the universe we tried to pretend didn't exist, but in the meantime people were still, like us, busily writing C++ code the world was running on. We just weren't talking about it so much. We're shining light on all of that goodness again. In the midst of all of this happy talk, there's some sobering talk as well, which continues the happy talk, but it's a little sobering. So we talked about our next decade or so of C++ Renaissance. What comes after that? Well, as I think it was Yogi Berra said, prediction is always hard, especially about the future. Ask any weatherman. But let's try. This is the decade that we're 2 years into now. C++'s fourth decade, where performance per watt is again king, performance per dollar. Is that a long-term trend, or is this just a blip and then we'll go back to business as usual in the 1990s and 2000s? It's been talked about. It's been prophesied many times failingly. But Moore's law is going to end. Every exponential progression has to end. There are only so many fundamental particles in the universe. Exponent has got to end, got to tail off. You've seen Slashdot articles for a decade saying, Moore's law is over, sky is falling. Well, people have been saying that. They weren't right, but they were right that it's going to happen someday. Now, the interesting thing about this is people seem to have this expectation that when a great run ends, you're going full tilt, and then suddenly, boom, you hit a wall, like that you didn't even see coming. It's not how it works. You could always see the end of one of these things coming, because it's like mining. When you're doing mining, gold mining or silver mining or whatever you're mining, you get the mother lode, and it's lower cost per yield. You're getting good yield at lower cost. You're getting lots of ore out of the ground. But what happens when that mother lode's gone? You get the side fissures, and you start mining them. It costs more. There's more other rock to sort through. You got to drill more to get less ore. And finally, there's still ore in the ground, but it's not commercially worthwhile to exploit anymore. So you don't just go from mining the mother lode one day to the tap turns off. That's not how it works. When you start to see the trend of diminishing returns, that tells you that yes, the end of that progression is in sight. Multicore was the first of those. Because for 30 years, we were able to exploit Moore's law to get more transistors at a decent power and production budget to run a single-threaded app faster. That was a great ride, that free lunch, 30 years. Now we're into new free lunch applications where you make them multi-core scalable. And now again, the application runs faster on tomorrow's hardware, the same binary, great. That's going to run about 10 years. Do you see a problem here? We're retooling the whole industry. We just finished retooling the whole industry to take advantage of multi-core. It's going to buy us maybe 10 years. Oh, and by the way, tomorrow we have a lot of talks about GPUs, which is now not just parallel, but heterogeneous parallel computing. That'll buy us another 5. In fact, I don't remember if I added this slide, but there's a harbinger here. Remember earlier, on one of the earlier slides, I said power is a main issue, performance per watt. And you might have noticed I used the word on die. Even on the CPU die, power is important, because we've turned a corner in the last couple of years. For the first time in our industry of microprocessors, we can no longer afford to send power to the whole chip. As we continue to scale down, we will be able to power less and less of the chip. When I was giving the keynote for C++ AMP in June at the AMD conference, the AMD Fusion Summit, one of the other keynoters was Jem Davies from ARM, who knows a thing or two about processor design. This is ARM. This is the processor that with Intel rule the world, that everything runs on, all the cool stuff runs on. And he gave an entire talk warning about how a lot of CPU design is now diverting power to the right part of the chip at the right time because we can't afford to power it all. Yes, we're still scaling the transistor count, but that's another case of diminishing returns. We are now able to power 92% of the chip. And you might have noticed this new paper that just came out in June at the International Supercomputing Summit, Dark Silicon and the End of Multi-Score Scaling, an excellent paper to read. Here's a new slide, excellent paper to read. It does projections based on models, and as soon as you say that, you should have as a grain of salt, a big one in your mind. Because yeah, okay, so they're doing computer models, and if we do this and we extrapolate this, but they're being fairly conservative, and they're clearly saying, okay, there are ways, here are the current problems, we need to find ways to break through them. They're not saying those ways won't be found. But on our current path, with known technologies, we're going to end up getting very little of, maybe another 7 or 8x performance increase in the next decade. Between now and 2024, it's even more than a decade. That's not the 32 we're supposed to have in that time frame. Now, they do point out that maybe there are ways that by really smart and diligent invention and engineering, chip manufacturers can pull a rabbit out of their hats again, just like they have in the past. Say, oh, here's these predictions, you can't do it. Look, we just invented this, see, we can do it. They've done this before. They may do it again, but they're getting less and less time to do it. Because to solve that problem, they have about 5 years, not 15. And so we're seeing those diminishing returns. What happens when Moore's law goes away? Tectonic shifts in our industry, but also performance per watt, performance per transistor gets more or less important. It is a long-term more important, and efficiency-oriented languages have a long-term future because only that efficiency, as well as I'll talk tomorrow about scaling out, distributed, are the only long-term paths beyond another decade or so to get the performance increases that we're used to seeing. And so we'll see what effect that has on us as code, but there is a silver lining because it's very good news for native code, which is all about performance per watt, per transistor, and per cycle. So the question shouldn't be why C++, the answer is why C++, of course. That's the answer to what you need for demanding applications. So welcome to C++ and beyond. Any questions about anything that we just said for a couple of minutes before we go to how to teach it? Where do I view Objective-C in this universe? Does it have metadata that's required? No. Does it have garbage collection that's required?
I'm not saying where do you see it fitting into which bucket.
Oh, but this is a good question. It's a good question because you're asking where does Objective-C fit in this universe? So does it have metadata that's required? No. Garbage collection that's required? No. It does reference counting and some medium support for that. If you look at it, it's largely a native language. So it falls in a similar bucket to C and C++. So all of the things that we've been talking about for power and performance are largely true there, except that C++, of course, has been much more about efficiency from the get-go, efficient abstraction, where it still holds a clear advantage over Objective-C in terms of templates and being able to make everything disappear, all the abstraction disappear that you didn't actually need or care for. Andre is the master at that, and we'll talk about variadics a bit more later this morning. So that's roughly where I see it, but I still see C++ with a really significant edge among those native languages. So Objective-C has some advantages over C++, and can you get those in C++ libraries? Now, the clear thing we are missing is a widely available standard C++ library that is large and rich, like the .NET frameworks, like the Java libraries. That is the biggest hole in C++'s story today. And today the answer is standard library and Boost. And 90% of people are allowed to use Boost. We need to do better at that, so I'll personally be working on that over the next year. But we need to define a much healthier standard library. That is the biggest thing that's missing. And to include doing many of those things like the message passing infrastructure and all of those things that are available in C++ libraries, but you can't count on them being portable, which is a problem today. So you can have named arguments and arguments in different orders. All of those things are sugar. You can build the language around them without changing the fundamentals. So it's an interesting point, but it's also worth seeing. Bjarne has never done efficiency without productivity. He's just never done productivity at the expense of efficiency. If you looked at all those C++11 features, a large number of them are purely productivity. They don't really increase your performance at all. They don't increase your code compaction at all. They're all about usability, like being able to declare explicit override and delete on virtual functions and automatically constructed methods, to have auto for type deduction, the new for loop. Many of those have nothing to do with efficiency, but you can have a lot of productivity too. So I think that falls in that category. It's a perfectly valid thing that we can learn more from other languages that have done some things better. But those can be added to C++ without diluting its core focus, which is interesting, and we've seen some of that happen in C++ OX.